For IQE number 5 through 8, I made a table of my revisions, and I'm going to better explain them through my solutions of the concept questions and calculation questions. For IQE number 5, I added more to the calculation question of IQE number 5 to find KL, which is the friction loss, the Reynolds number, and the pressure loss of the air duct. I recalculated the change of the pressure loss and explained why the flow is turbulent. I better explain my solution to my IQE to better understand my solution. I also added to my conceptual question due to the complexity or lack thereof, and I better answered the conceptual question. I explained the key concepts in my video that I'm currently doing right now. Because I turned in IQE number 5 late, like really late, Marley Garman was able to peer revise my IQE, which helped a lot. For IQE number 5, we know that air at 20 degrees Celsius in one atmosphere have these chemical properties. It flows through an air duct with an initial diameter of 15 centimeters and an exiting diameter of 10 centimeters. The air duct is a 40-meter long duct at an average velocity of 6.6 meters per second flow. The air duct has various flow restrictions, and a total minor loss coefficient will need to be found. The friction is 0.035, and we need to determine the pressure loss, the coefficient, the Reynolds number, and is it laminar flow and turbulent? Why? For the conceptual question, what would be the effect of an elbow throat on the turbulence within an air duct if it is a sharp throat or a rounded throat? I added this to my conceptual question. Why is it important to know the friction coefficients of different types of elbow throats? Would the friction coefficient be different with different flows, turbulent, or laminar? Elbow throats consequently reduce the turbulence of the airflow within the air duct. The sharp 90-degree throat will cause more turbulence, while the rounded 90-degree throat will result in less turbulence due to the friction losses from the inner surfaces as well as the flow going around the bend. It is important to know the friction coefficients of different types of elbow throats because it shows the amount of friction existing between two surfaces, and different fittings can decrease the pressure flow within the pipe. Laminar flow has a low coefficient of friction, meaning that less force is required for flow to come through. The turbulent flow requires more force, thus a higher coefficient. For my calculation question, I did the K-FAPS, which is known, find, assume, and solution. So we know that it's a 40-meter long duct. That's the length, L. We know that the velocity average in the positive x direction is 6.6 meters per second. We know that diameter 1 is 15 centimeters and diameter 2 is 10 centimeters. We know that the temperature of air is 20 degrees Celsius. The friction coefficient is 0.035. It was stated the viscosity and the density, but you can also find it in table A1, air properties. We need to find the coefficient loss, the pressure loss, and Reynolds number. We can assume steady state, constant density, incompressibility, no work, and it is a horizontal duct, so flow is only in the x direction. For a change of pressure loss, we know that it's F times LD, which is the 40 meters. I did an average of the diameter plus KL, the coefficient loss, or the friction loss, which I solved right here, times 1/2 density times velocity squared. So to get the friction loss, it's 1 minus D1 over D2 to get a 1.5624 KL. We can plug that back into the change of PL to get a 50.71 PA of a pressure loss. To check to see if it's laminar, we need to do a Reynolds number. We need to calculate the Reynolds number, which is RE equals density times diameter times velocity over viscosity. So we know that the density is 1.204 times 0.1 meters times 6.6 over 1.825 times 10 to the negative 5 kilograms meters per second. We get a Reynolds number of 6,553.0 0.29. Therefore, it is turbulent flow because Reynolds number is greater than 4,000. Now, if it was less than 2,000, it would be laminar flow. But if it was in between 2,000 and 4,000, it would be transitional flow. For my IQE number 6, I added the statement, if the sunflower seed will be moving in the X direction, the drag force would also shift accordingly. I calculated the Z direction acceleration to show the acceleration of the effects it would have on the seed if the seed didn't fall directly down, but had some direction in this Z axis. I better explain what each step I did in the solution, which I'm doing currently, and why I used each equation in the recorded video. There was no comments on the justification section though, so even though I got a 0 on it, I changed what I thought I needed to change. It was just quite difficult to do that. For the calculation question, you have all of your properties stated, and I have X direction. What I added was what would be the acceleration of the seed in the Z direction when it blows 60 degrees to the right, which is a positive blow, not a negative blow. So the velocity will be in the positive direction, not the negative direction. The conceptual question. If the breeze increased to a steady 5 miles per hour wind, what would happen to the drag force acting on the sunflower seed and why? The drag force will decrease in the Z direction, eventually becoming negligible to the sunflower seed because the relative velocity of the air will be enormously greater than the relative velocity of the sunflower seed due to gravity, since the sunflower seed is moving with the air in the X direction. Okay, we know it's important, it has to be in the X direction. For the solution, I did the K-FAPs as well. So we know the velocity of air x is 0.95 meters per second, and the velocity of air z is 4.5 meters per second. We also know that the diameter of the sunflower seed is 0.0636 meters, and we know that the density of the sunflower seed is 415.4 kilograms meters cubed. This is all research, so it does have it. So to get a vector force, we have to kind of do a diagram showing where it would be and why it's to the right. We have force C going down and we have force X going to the right. We need to find the initial acceleration in the X direction of meters per second squared and the Z direction acceleration. We can assume that the air temp is 30 degrees Celsius because it was stated in the problem statement, and the air pressure is at 1 atmosphere. We can look at the properties, table A1, to get density of air as 1.164 kilograms meters cubed, and the viscosity of air at 1.872 times 10 to the negative 5th kilograms per meter second. In this blue, if the sunflower seed will be moving with the air in the X direction, the drag force would also shift accordingly. So there will be more drag force when it's going directly this way, but if you're having that, there's drag force in the X and Z direction. So we had to calculate Reynolds number, which is R equals density times diameter times velocity over viscosity to get 375.68. We also had to calculate CD, which is 24 over Reynolds number times 1 plus 0.158 Reynolds number to the 2/3 to get a 0.589419. To get the force drag, it's 1/2 CD times the density of air times the area projected, which when calculated, we can calculate the area being projected from the seed, and times velocity squared over 2. So we can calculate that within the whole equation. So it's pi times 0.00636 meters per over 2 squared times the velocity to get 4.9177 times 10 to the negative 6 kilograms meter per second squared, which is a Newton. To get the force in the X direction, we already found that. That's the force drag, but we need to find acceleration. So we know that force equals mass times acceleration, and acceleration equals force drag over mass. To calculate mass, it's mass time equals density times volume to get 5.5954 times 10 to the negative fifth kilograms. We can plug that back in to get 0.087 meters per second squared. Okay, this makes sense because it's a small volume, which means there's a small surface where the air can grab the seed to get a small velocity in the x direction. So we already know that the z direction acceleration is at a 60-degree angle, so we can calculate the velocity at with 4.5 meters per second times cosine 60 to get 2.5 meters per second. For the force drag, it's the same idea as the x direction, just for the z direction velocity to get 2.437 times 10 to the negative 6 newtons, or kilograms meters per second squared. Then we can find that acceleration to be 0.0436 meters per second squared because we already know the mass and we found the force drag. For IQE7, it was difficult. I found it very difficult to revise my IQE because there was like little to no useful comments to edit in the IQE. Most of it was you did a good job, but then my scores would say something different. It would have a lower score. I went back to see if all my knowns were listed from the problem statement, and I didn't find anything that I missed. I could have missed something, but I rechecked and added some. I explained my solution more in the video recording, as well as I added a constant density and flow is incompressible to the assumptions portion of my IQE number 7. So IQE number 7 is porosity media. I did a water trickling from a faucet onto a sponge that's over the drain. So what impacts does the porosity have on the water trickling down to the drain? This is my conceptual question. The porosity of the sponge adds friction over the drain, allowing the velocity of the water from the faucet to significantly slow down, which then allows the sponge to soak up the water, and this creates the fluid flow to become super low, which implies that the flow is laminar, the flow is near to a solid boundary, the sponge has a constant direction of flow. For my solutions, we know that the known is that the diameter of the faucet is 1 inch. We know the sponge has a length of 3.5 inches, width of 5 inches, and a density porosity of 0.05 inches, which equals E equals 0.85. Or diameter porosity, sorry. That can get us to 4.1667 times 10 to the negative 4 feet and have those dimensions. We know that the sponge is 1.5 inches off the drain, and the length in total from the spout to the drain is 14.25 inches or 1.1825 feet. We can assume that it is laminar using Darcy's law because it is trickling down. When it trickles, that means there's not as much velocity. That means there's not going to be as much fast flow. So we can do friction equals 150 velocity times viscosity times 1 over porosity squared over 1 minus porosity squared times the diameter of the porosity cubed or squared times porosity cubed times the length over density. We need to find the velocity stationary, the volume, the RP, the RE, and then K. We can assume that it's negligible kinetic energy. The change of pressure through the sponge is negligible because of it being trickling down. It's laminar. It has it's incompressible flow, and it has constant density. For the properties, we know that the density of water is 62.3 pound mass per feet squared, and the viscosity is 6.75 times 10 to the negative 4th pound mass per feet second. We can start off with the Bernoulli's equation because it's incompressible. There's constant P, it's at steady state. To get P1 over density plus GZ1 plus V1 squared over 2 equals P2 over density plus GZ2 plus V2 squared over 2 plus friction. We can neglect the friction because we're ignoring KE, kinetic energy, so or not friction, the velocity of V1 and V2. We can cross out Z2 because it's 0, because Z2 is right here, point 2 is labeled right here, and point 1 is labeled right there. So to get the friction, we know that friction equals GZ1 to get a friction of 38.2375 feet squared per second squared. We know that this is 1.1872 feet because that is the height of the faucet to the drain. Vs is friction times diameter porosity squared times porosity cubed over 150 viscosity times 1 minus porosity squared times density over length to get a Vs of 0.0941887 feet per second. We know, then we can find the volume metric flow, right, by multiplying Vs and the area projected. The area projected is within the sponge, so you can figure out what the area is converted to feet, which the dimensions are right there, to get 0.0114 feet cubed per second. The REPM is calculated by density times diameter porosity times velocity over 1 minus porosity times viscosity. You get 24.21992. This is laminar flow because it is low. Laminar does dominate, which makes sense why we can assume laminar with Darcy's law. If it was too high, we can't assume Darcy's law. Now to find K equals the diameter porosity squared times porosity cubed over 150 times 1 minus porosity squared to get 3.16 Darcy's, which is equivalent if you do Vs, velocity S, times viscosity times length over density times friction to get 3.16 Darcy's. So these are very equivalent. It doesn't matter how you get K. For IQE number 8, I relooked at the videos in the lecture, but I didn't find anything in the example. In my graded rubric, it said that it was very similar to the example, and I looked at it and I didn't find that. I discussed how K changes with temperature in the video recording, which I'm going to do right now. I made it more clear in the concept question solution that air is assumed to be ideal and diatomic. I explained why MA equals 1 is valid in the video recording. I added to the answer to the conceptual question, and I redid CE using the correct R to get the velocity more reasonable at 58.4136 meters per second, which is a laminar rate or laminar flow. When I first calculated it, it was 280, which was turbulent, which didn't make sense for a tire puncture with a hole of 10 centimeters. So for IQE number 8, compressible flow, I explained my calculation question is basically you are driving and then driving on the highway, you run into some construction and a nail punctures your tire, creating a hole. What is the velocity of the flow coming out of the tire, and then the approximate the choked mass flow rate exiting the tire. For the conceptual question, why can we assume the speed of sound can be approximated as C equals KRT over M to the 1/2 for an ideal gas? We can also assume it for something for other more complexities, but I want to explain it with the ideal gas. For an ideal gas, the speed of sound can be approximated by the equation above. When the fluid flow of the air is reached at a Mach number of 1. It is safe to assume that the K number is 1.4 for the air at ambient temperature, which is 25 degrees Celsius, though you can still use the equation for C to solve the diatomic or complex gases because there is still a CV value at a different temperature for each K. For each gas, K is dependent on temperature, so it would change if the CP and CV values would not be constant. But since the question is just asking for ideal gases, the K value is assumed to be constant. So it would be a valid equation for diatomic or complex gases. Then in an ideal situation, K is independent of temperature. When it is a diatomic gas or more complex gases, the K will depend on temperature, therefore decreasing when the temperature is increased. We know that the theory is that as temperature increases, K will increase. But that is for more of an ideal situation than a more complex or diatomic gas. For my solution, my knowns are the PC of 240 kPa, the T initial of 298.15 K, and the velocity is assumed to be 0 meters per second because there is no hole right now. We know the diameter of the tire is 16 inches, which equals 0.4064 meters. And we know that the hole is 10 millimeters, which is 1.0 times 10 to the negative 4 meters. The pressure atmosphere is 101.325 kPa. We need to find the velocity and the mass flow rate. We can assume air is at 25 degrees Celsius. We know that CP over CV equals K equals 1.4. We know that is a compressible flow. There's constant CV and CP, negligible change in potential energy, and it's isentropic. The properties is CP equals 1.005 kilojoules per kilogram Kelvin. CV is 0.7180 kilojoules per kilogram Kelvin, which gives you that 1.4. We know that R is 8.314 joules per mole Kelvin. We know the molecular weight of air is 28.97 grams per mole. If you divide by 1,000, we can get kilograms per mole, which is 0.02897. So if the pressure of the tire is greater than or equal to the pressure of the atmosphere, if it is below the pressure of the tire, it will be choked. Then we can assume that that the Mach number equals 1. So when we calculate the pressure of the tire being from the hole, if it is below what is originally in the tire, we can assume that the Mach number is equivalent to 1. So we would multiply 101.325 kPa times 1.4 plus 1 over 2 to the 1.4 over 1.4 minus 1 to get a pressure of 191.801 kPa, which is less than 240 kPa. Therefore, it is choked, so the Mach number has to be 1. I then calculated the absolute pressure, which equals 431.801 kPa. I also calculated the area to be 7.834 times 10 to the negative 9 meters per second squared. This is because to get the mass flow rate, we need the area projected, or the area that is created by the hole, and we need the pressure initial. So we know that the mass flow rate choked is area times pressure initial times the square root of K times molecular weight over RT initial, which is temperature, times 2 over K plus 1 to the K plus 1 divided by 2 times K minus 1. When we plug in all the numbers, we get 7.939 times 10 to the negative 9 kilograms per second. Then we can get CE, which is the square root of KRT, since the Mach number is equivalent to 1. And we don't have to divide by the molecular weight to get a CE of 58.4136 meters per second. We know that MA equals V velocity exit over CE. When we rearrange, we can find for the velocity exit to get 58.4136 meters per second, which sounds to be more correct, and therefore it's a laminar flow and it is less than the speed of sound. Thank you.